So all the chapters kind of so far have been pretty much all over the place because we've kind of got to get your basis down. Now is when we finally start actually going back to stuff that we've done before and using it. So we are just going to deal with essentially what we did yesterday, but today is only with proportions. So each dot on the graph is a p hat. So it is a sampling distribution of sample proportions. We talked about this yesterday. If we had the true sampling distribution, the center of that sampling distribution compared how to the population. So we had 4 yellow, 3 blue. So what was the overall population parameter for yellow? 4 out of 7. When we took our sampling distribution, which was all of the possible samples, and took the average of all of those possible samples, what do we get as our mean? 4 out of 7. Exact same thing. So the mean of the sampling distribution, it is the mean, so that is mu, but it's the mean of your graph made up of all of your p hats. So it is the mean of the sampling distribution of p hat. And we said when we do this, that equals the actual population proportion, which is what symbol? What symbol for population proportion? Correctly if it's unbiased. So what do you think our symbol for standard deviation of the sampling distribution is going to be if that's mean of the sampling distribution? Sigma of p hat. This one ends up being square root of p times 1 minus p over n. For our class, we don't get into the derivation of this, but essentially it's very similar to binomial, which is square root of n times p times 1 minus p, accounting for sample sizes, because we're taking a sample of and not just one. But we don't have to get into the derivation of that.
I don't really get why we have the p hat beside the mean thing.
So it's the mean of what? It's the mean of our graph made up of a whole bunch of p hats. Like, remember yesterday, each dot on our graph was a p hat.
Yeah.
That's essentially what that's saying.
That equals p.
So this is yesterday, the mean of all of our p hat dots gave us 4 out of 7, which is the same as the actual population, which was 4 out of 7.
So that equals the mean of the sampling distribution?
Yes. So this is the mean of the sampling distribution, which should be the same as the mean of the population.
Okay.
Alright, so this is one thing that I talked about yesterday where I said using this sample of only 7 wouldn't actually work, but you don't know why. This is where it comes in. So we can only use this equation if something applies. Very scraping the top of the surface here. When we find like a sample standard deviation versus a population standard deviation, we divide it by n minus 1 because we account for error, right? That kind of thing is going on here. So we are accounting for error that occurs. Well, let me write this first, and I'll finish explaining that. What does that symbol mean?
Number of trials.
Number of trials or population size. So our population size has to be at least 10 times as big as our sample size. We are accounting for error as though we're not sure if we got the dots that are the farthest away or the closest or somewhere in between. if our sample size gets too close to our population size, we're accounting for too much error that can't be there. Y'all don't need to know that background part, but that's essentially where this is coming from. We're accounting for error. We're taking too much of, so like yesterday, taking 5 out of 7 would not have worked here, which means I couldn't have used that equation. Let's just write population.
We also have very little room already.
I know, I'm not writing much. 10 times bigger. So when we take more and more samples, our distribution starts to get symmetrical, which we kind of showed a couple days ago. Last week, maybe. As it gets larger and larger, the sampling distribution gets closer and closer to a normal distribution, which is with mean that we had up there, which is mean p, standard deviation, which is what we had up there, which was p times 1 minus p over n. I'm just saying the same equations we just came up with. Now, this is when our sample size is large. What does it mean to be large? We talked about this one during last chapter, but I told you you don't need to know it at that point. If our n times p and our n times 1 minus p are both greater than or equal to 10, then we can use a normal approximation.
Where did you get where did you get the equation for the standard deviation? The p 1 minus n over n?
Right there.
Then where'd you get that from? I didn't understand.
That's derivation outside of what we need to deal with this class. It's essentially like your binomial is square root of n times p times 1 minus p, which is very similar to that, but we're accounting for the fact that we're taking a sample, and that's.
Were we supposed to know that? Yeah. Okay, I'm learning now.
Alright, so we're going to apply these things to an actual problem. So Gallup poll once asked a random sample of 1,540 adults who happen to jog. Suppose that in fact 15% of all adults jog. I didn't leave you space for this, and I don't need you to write this, but what would our population be here?
Adults.
What would our sample be here?
Adults asked by the poll.
What does this number represent? What symbol? Because it's of all, so that is our P. And like I said, you didn't have to necessarily write that, but I just wanted to go over as we're going. So find the mean and standard deviation. So first with mean. So this is the sampling distribution of p hat. So what is my symbol for the mean of the sampling distribution of p hat?
X.
U of p hat. Well, I know that mu of p hat equals what? P, and what do I know that p is? 0.15. For standard deviation, what is my symbol? I will say this is the first day. Now this is the day one of what starts to be, but things start to get very repetitive which has not been the case of literally anything in our class so far. So you've got to make sure that you know this stuff up front, because then it just kind of keeps repeating over and over. What's our equation for sigma p hat?
That's 1 minus p over it.
P times 1 minus p over n.
That's 1 minus.
So what is p? I usually go ahead and do the math for 1 minus. What's 1 minus? What was our lowercase n for this problem? If you haven't gotten a calculator yet, and you usually get one, they're on my desk. From now on, just pretty much grab one as you walk in. I don't think there'll be another day where we don't use them. And what do you get for decimals?
0, 0.
But only if 10% condition. This problem, since the first one we're doing, specifically asks you, how did we know we could use that? Usually it's not going to, and you're going to have to write it there. I'm going to answer this question and then go back and write it up there. So what do I need to know to be able to use standard deviation equation? What? The 10% condition, which is capital N is what?
Greater than or equal.
Which one of those do I know? Lowercase n. Which just gives me 15,400. What does the capital N stand for? So in this particular case, it's all adults. So are there at least 15,400 adults?
Yes.
Yes.
But not 16,400.
Huh? In general. This is just all adults. So we're going back to what we would have written as our population.
So big N means
Population size. So I've checked this now, so I would have needed to write that there that, hey, I use this because this worked. So we've got a mean, we've got a standard deviation. It was okay that we use that standard deviation equation.
yes.
So now I want to know if we can use a normal approximation. So what do I need to test to see if it's normal?
Sample size has to be bigger than
N times P has to be, and
N times 1 minus p.
what's our N? What's our P? What's 1 minus P? What is 15% of 1540? Which leaves how much over here? So this is saying my sample. This is saying my successes. This is saying my failures. So it's basically saying there are at least 10 successes and failures in my sample. There are at least 10 sampled adults who it's technically should be, but you don't have to worry about that. Both. What are we deeming a success?
Jogging.
Or what answer again? Oh, it does say do jog. And at least 10 who do not jog. So there are at least enough of each so we can use a normal approximation. But you have to write that. This is one thing that will count off. If you say, so it is normal, that is wrong. Because that is saying it exactly perfectly fits that curve exactly how it should be. We are not saying that. We're saying it is close enough to where we can use this as a guess. So you have to say the word approximation. So now we know we can use normal. We have a mean, we have standard deviation. Now we're essentially going back to what we've done before. So if I know that it's normal, and I know the mean and another standard deviation, can I find the probability? Yes. So we're going to write this out. What symbol is that talking about? What's percent of the sample? P hat. So we are saying that our P hat is between 13% and 17%. Well, when we did this before, we had an X there instead of a P hat. Now we're just starting with something different. So once I have these values, I have to convert them to what? Z-scores. What's our general equation for Z equals?
Loss value minus mean.
What's our value here? We've got two of them, 13% and 17%. What is our mean for this whole problem? 0.15. What is our standard deviation for this whole problem? 0.0091. So we're going back to what we did in chapter 2 here. So what's our value when I'm doing it for this one? So 0.13 minus our mean, which is 0.15,
Where are we finding two different t-scores?
one for this, one for that, divided by and what does that give you?
-2.197.
And this is a z-score, so using our table, we always round the z-score to how many? 2. The z-table only has 2 decimals. So it rounds to negative 2 point. So then I have to find a z for this one. What number should I plug in here? Minus. Everything else stays the same, divided by 0.0091. Well, I was 2% to the left, now I'm 2% to the right.
So it should probably be like 4. No, 0.
It's the same thing, just positive negative because our graph is symmetrical. It's only going to work out if it's the exact same distance from the mean both directions.
It doesn't
And
matter if it's like 5 or
Right.
4.
so I get what here?
2.2.
Just to kind of show you why I make a big deal about rounding to so many decimals. If I rounded my standard deviation to 3 decimals instead, and just did 0.009, which doesn't seem like much of a difference, my z-score changes to 2.22. And if I did it to 2 decimals instead, and just did 0.02 divided by 0.01, it would change to 2, which changes it a whole lot. So a tiny little bit here with decimals makes a huge difference percentage-wise. So that's why I go to 4 when I can. Alright, so at this point I've got both my z's. What do I need to put on my paper? What do I need to show on my paper? What?
Probability, when we rewrite it, the probability of some z-score, that thing that you less than z.
So that's the exact same process before. This is what I want to find the probability of. I'm going to convert those to z's, and now I'm going to rewrite it in terms of z's. What else do I put on paper? Reference line for 0. I've got one over here at negative 2.20. I've got one over here at 2.20. And where do I want to shade? Because the wording of the problem tells me I want between. Questions right now? This is stuff that we've done before. Alright, so then we do, when z is negative 2.22 or 2.20, what is our area? And I've shown you another way to write this, so I'm doing this in red on purpose. What do we get as our area when we look up the z-score of negative 2.20?
0, 1,
0, 1, what?
3, 2.
When I look up z equals 2.20, what is my area?
The first one's 0.13.
0.139.
Yeah.
Okay, and then what do I get as my upper bound?
9.861.
And what do I do with those? Which gives me
0.9722.
0.9722. I showed you this once and said you can use it if you want to, but you don't have to. And then we went straight into the test, and I don't think most people used it, and then they forgot about this. So I want to show you again. In your calculator, go to second distribution. What is the first thing that's there? Things that start with what? Normal. We don't use normal PDF. We only use normal CDF. So this is saying I want a normal distribution with a lower number and an upper number. Well, what is my lower number here? And what is my upper? So it should look like that. The 0 and 1 always stay because that means it's standard normal, which means we can use yellow sheet. And when I hit enter, it gives me 0.9722, which was our answer. So this is the calculator's way of doing the yellow chart for you. Now, you can still continue to use the yellow sheet, and that is absolutely fine, but you also have this resource if you would rather do it this way. Questions? Okay, I know we have one problem left on the left side, but by the looks on your faces, y'all aren't ready for it. That's fine. Let's go ahead and go straight into practicing. So I'm gonna